So now that we've got our notation down, we're going to start approximating the area under the curve. Now, we're going to cover two different ways to do that in this section. There's what's called left endpoint approximation, and then there's right endpoint approximation. We're going to start off with left endpoint approximation. And basically what this says in the box, we're going to approximate the area under the curve by creating rectangles. And we're going to create the rectangles by taking that interval from A to B. So here's our interval from A to B. And we're going to break it up into subintervals of equal length. Now, how many subintervals we're going to create? That's up to you or as the question specifies. And the number of rectangles that we're going to use is indicated with the notation n. So we're going to create n subintervals. And then we're going to figure out the width of the rectangle by dividing the length of that interval by n. That's going to give us the notation delta x. This is going to be the width of the rectangle. And we get that by finding the length of the interval AB and dividing it by n, however many rectangles you want. The notation that this book uses for left endpoint approximation is ln. And so if you look at this picture, to find the height of the rectangle, you're going to look at the left edge of each rectangle. That is why they call this left endpoint approximation, because we're using the left top corner of that rectangle to find the height of the rectangle. Now, so what you're going to do is you're going to evaluate function at that value of x to find the height of the rectangle. So if this is our first point, x0, then we'll call this x1, and we'll call this x2, and this x3. So we have, in this case, 4 rectangles, and we have 1, 2, 3, 4 points. When we plug each of those 4 points into our function, that's going to give us the height of each rectangle. So then if you go back up to this notation, this is going to give us the height of the first rectangle. When I plug x sub 0 into the function, that's the height of the first rectangle. Then you multiply that by the width of the rectangle, which we said is delta x. Then you do that for each rectangle. So then I plug in x1 into f. That will give me the height of the next rectangle. And then we multiply it by the width of the rectangle. And then we keep doing that and we add up all of those. And then what we get for the notation is this. We're just going to add up all of those rectangles by plugging in our x values to find the height of the rectangle, because that's right on the function, and then multiply by the width. The same idea goes for the right endpoints, only now when we look at the picture, here is our function. We're going to be using the right-hand point of the rectangles to evaluate the function to find the height of that rectangle. The width of the rectangle is still going to be delta x, and they should all have the same width. Our notation for right-hand endpoint approximation is going to be Rn. Other than that, it's the same idea. Then we add up all of those areas of the rectangles. There are 2 other vocabulary terms that you need to be aware of. This picture A, represents what's called a lower sum. And picture B is what's known as an upper sum. The difference between the two is, if you notice, the rectangles, and we'll look at A first for the lower sum, the rectangles fall below the curve. So when we add up all of our rectangles, we have this space here that I'm highlighting in navy blue. That space there is unaccounted for. So it's going to be an underestimate. When I look at the picture for graph B, notice that my rectangles are above the curve. So we have this extra area here that we're going to add up when we add up all the sums of the rectangles. So this is going to be an overestimate. So that is the difference between the lower sum and the upper sum. When you're calculating a lower sum, it's going to be an underestimate because you're going to have a little extra area under the graph that you haven't counted. And the upper sum is when the rectangles come up over the curve and you're going to get an overestimate because you have some extra space in those rectangles that you're counting in the area. Now let's walk through an example on how we can approximate the area under a curve. So in this example, the question wants us to use both left endpoint and right endpoint approximations to find the area under the curve. We're going to use the function x squared, and we're going to do this on the interval from 0 to 2 using n is equal to 4. So that n is equal to 4 tells us we're going to break it down into 4 subintervals, which also tells us we're going to have 4 rectangles. So the first thing we're going to do is divide the interval from 0 to 2 into 4 subintervals. So to figure that out, we're going to take the length of the interval. So we're going to take 2 minus 0 to find the length of the interval, and then we're going to divide it into 4 equal subintervals. When we do that, we're going to get 0.5. So this tells me the width of the rectangles. And we label that as delta x. So if we draw a sketch, x squared looks like this. And if we're looking from 0 to 2 on that interval, and we split it up into 4 subintervals with length of 0.5, here's what it's going to look like. Now, we're going to start off with left endpoint. So that means when I draw my rectangles, the left point is going to touch the curve and represent the height of the function. So when I make my rectangle here, my left point is touching the function. And that way we can use that point, 1.5, to plug it in to find the height of the rectangle. Here's the next rectangle. I'm going to come up, use my left point, and that's going to give me the height of the rectangle. Next one, I've got this. My height at 0 is 0. I can't make my fourth rectangle. So now I'm going to label this L4 because I'm using the left endpoints and I am using 4 intervals. I'm going to call this x sub 0, x sub 1, x sub 2, x sub 3. So these are the points that I'm plugging in. So I'm going to take f of 0 times 0.5. That's going to give me the area of rectangle 1. Although it's not really there because we couldn't build it up because the height would be at 0, we're going to write it down so we can practice. So then to find the second rectangle, to find the height, I'm going to plug in f of 0.5. And I'm going to multiply by the width of the rectangle, which is 0.5. That's going to give me the area of rectangle 2. So I'll label it up here. To find the height of my next rectangle, I'm going to plug in 1. So I'm going to have f of 1 And I'm going to multiply that by 0.5, which is the width of my rectangle. That's going to give me area of rectangle 3. That's this one here. And then the last one, I'm going to take f of 1.5, multiply it by 0.5, and that's going to give me the area of rectangle 4. Now, when I plug in 0 into the function, which is x squared, let me remind you that f of x is x squared. That's the curve. That's going to give me 0, and 0.5 is 0. That's why we have an area of that rectangle is 0. When I plug in f of 0.5 and I square it, that's going to give me 0.25. And then I multiply that by 0.5. The next rectangle, if I plug in 1 into x squared, I'm going to get 1. And I'm going to multiply that by 0.5, and that will give me the area of the third rectangle. Let me label this. This is for the first rectangle, second rectangle, third rectangle. Now for the last rectangle, to find the height, we're going to plug in 1.5 into x squared. We're going to get 2.25, and I have to multiply that by 0.5. And that will give me the area of rectangle 4. Now, when we add all of that up, we're going to get 1.75. So that tells us an approximate area under the curve using left endpoints. Now, doing this for right endpoints, we're going to have the same function x squared, but we're using right endpoint approximation. So here's 0, here's 1. Now, since we're using right endpoint approximations, when I draw my rectangles, my right upper corner is what's going to touch the function. So now I'm going to add up the area of my rectangles, and I'm calling this R4 because we're doing right endpoints, and we're doing it with 4 subintervals. So I've got to plug in f of 0.5 times it by 0.5 plus, I'm going to copy it down here because I don't have a whole lot of room. So these are now my endpoints. So I'm going to plug in now for the second rectangle, f of 1 times 0.5 plus f of 1.5 times the width of the rectangle, which is 0.5, plus, and lastly, f of 2 times 0.5. So this is going to give me 0.25 times 0.5 plus 1 times 0.5 plus 2.25 times 0.5 plus 4 times 0.5, and we're going to get 3.75 when we add all that up. Now, notice that when we did the right-hand endpoints, that we had this extra area up here. The rectangles went above the curve. So this is going to be an overestimate. And then if we look up here, when we did the left endpoints, we had extra space here that we didn't count. So this is going to be an underestimate. So if I were to make a guess and try to get more accurate with my area, since I know 1.75 from our left endpoint approximation is an underestimate, and I know that 3.75 from our right endpoint estimate is an overestimate, I can guess that my actual area is going to be somewhere between 1.75 and 3.75. Now let's take a look at this GeoGebra animation. I wanted to show you and illustrate how the more rectangles that you have, the better your approximation is going to be. So let's say under this curve, I want to find the area from 2 to 3. So I'm going to set my A at 2. I'm going to set my B at 3. Let's say I want to estimate this using 3 rectangles. Now I have the box checked for left endpoint rectangles. I'm going to hit enter, and notice I have 3 rectangles here, split it up into even subintervals. And when I look at this is definitely going to be an overestimation using the rectangles because I got area above the curve that the rectangles go over. Let's see what happens when I pick 4 rectangles. So the width of those rectangles got smaller. Now look at the area above the rectangle. It got a little bit smaller. Let's do 10 rectangles. Notice the more rectangles I have, the closer this is going to come to the less error I'm going to have. If I go to 20 rectangles, there's less and less area that goes above that curve with the rectangles. Let's go up to 40 now. So the skinnier my rectangles, because I have more rectangles and I break it into more and more subintervals, it gives me a more and more accurate area under the curve. Is it more work? Yes. If I have to find the area of 40 rectangles, that's more work, but it's going to be more accurate. Now let's go back to 4 rectangles. So that area above the curve will give us a much bigger error versus the 40 rectangles. Now let's look at right endpoint. So now my rectangles are going to switch, where the height of my rectangles are going to be determined by the right side of the rectangle, and that's where it's going to hit the function. So now the right side of my rectangle hits the function, and so now this is going to show an underestimate because now we have space under the curve that we're not counting. So I'm going to go up to 10 now, and you can see that that area gets smaller. It shows the sum here off to the right as well. You can follow it where it says the sum is 2.297. Now I'm going to go up to 20 rectangles. So now there's less empty space that we're not counting, and our sum went up to 2.33. Let's look at 40. So now there's even less area that we're not counting, and my sum went up to 2.35. So you can use this application or this animation to visualize how the skinnier the rectangle is, and the more rectangles you fit under that curve, the more accurate your estimation is going to be.